So in this exercise we have a random variable x which has expectation mu x and variance 400, and we sample 100 observations from it in order to construct x bar our sample mean. Now the sample mean, because the observations are assumed to be IID, the sample mean will have a distribution such that the expectation of the sample mean is the same as the expectation of the underlying population random variable, because the sample mean is a unbiased estimator of the expectation of the random variable, and the variance of the sample mean is going to be equal to the variance of the underlying random variable divided by the number of observations. So in this case that's equal to 400 divided by 100, which is equal to 4. Now by the central limit theorem, provided the sample size is large enough, the sample mean will follow an approximately normal distribution. So here we've got 100 observations. That's sufficient for the central limit theorem to apply. So that means that the sample means are going to follow a normal distribution with expectation equal to mu x, the expectation of x, and variance equal to 4. Now, suppose that we've got a sample mean equal to 57. Now that might have been drawn from a population where the true expectation was equal to 50. So suppose that mu x was equal to 50. How would the sample means have been distributed? Well, if mu x, the expectation of x, was equal to 50, then the sample means would be normally distributed with expectation 50 and variance 4. And we can see that distribution here. Now, suppose we wanted to calculate the probability of getting a sample mean greater than or equal to 57. How could we do this? Well, one way of doing this would be by beginning by standardizing our random variable. We can see 57 marked on our diagram, and the probability of x being greater than or equal to 57 is the area under the distribution to the right of that dotted line. So now let's standardize our sample mean by subtracting the expected value of that sample mean and dividing through by the standard error of that sample mean, which is just the same as the square root of the variance of the sample mean. And that new variable would be normally distributed with expectation 0 and variance 1. So substituting the numbers in, 57 is the sample mean, 50 is the expected value, so our new observation, the z-stat, is 57 minus 50 over the square root of 4, which is 3.5. So the probability that x bar is greater than or equal to 57 is the same as the probability that a normally distributed variable with expectation 0 and variance 1 is greater than or equal to 3.5. So let's look for 3.5 in the tables. Well, the tables only go as far as 3.3. So the probability from the normal distribution tables that z is less than or equal to 3.3 is just 0.99952. So that means that the probability that z is less than or equal to 3.5 is going to be approximately equal to 1. But we're not looking for the probability that z is less than or equal to 3.5. We're looking for the probability that z is greater than or equal to 3.5. And in order to calculate the probability that z is greater than or equal to 3.5, that's going to be 1 minus the probability that z is less than or equal to 3.5. So the probability that z is greater than or equal to 3.5 is going to be approximately equal to 1 minus 1, which is equal to 0. So from that we can also say that the probability of getting a sample mean greater than or equal to 57 is approximately equal to 0 as well. In the final part of this question, we need to formally test the null hypothesis that the true expected value is equal to 50. So we specify our null hypothesis, our h0, that e of x is equal to 50, against the alternative hypothesis ha, that the expected value of x is not equal to 50. Now in order to test this, we're going to standardize our sample mean by taking x bar minus the expected value of x bar, conditional on h0, the null hypothesis being true, and divide through by the standard error of x bar, which is the same as the square root of the variance of x bar. And that z statistic will be normally distributed with expected value 0 and variance 1, if the null is true. So our z-score is 57 minus 50 divided by the square root of 4, which gives us a z-score equal to 3.5. Since the critical value at the 5% significance level is 1.96, our z-score is greater than 1.96, which means we can reject the null hypothesis in favour of the alternative. That doesn't mean that the alternative is true, that doesn't mean that the null hypothesis is necessarily false, but we can reject the null in favour of that alternative hypothesis at the 5% significance level.